Hello, everyone. We're Team RIST. We're a senior engineering team from Rice University, and RIST is an acronym for Wearable Radial Interface for Sensory Technology. Here's our team. We're composed of 3 mechanical engineers and 3 electrical engineers. In this presentation, we'll start by going into our project context and our mission. Ollie will talk a bit about some existing solutions, and then we'll talk about our design, summarize it, and then we'll go into the impact that our design could have. So our project is in the space of virtual reality. And as a growing industry, the ultimate goal of virtual reality technology is to closely replicate the experiences that we get in the real world, but in a virtual environment. Having realistic simulations of the world involves wide-ranging impacts for accessibility, skill development, and entertainment for industries from education, healthcare, aviation, sports, and more. In the real world, we have 5 senses to help us gather information about our environment and interact with it. In the virtual environment, the end goal is to replicate this same sensory feedback. However, current virtual reality technology incorporates only visual feedback, audio feedback, and limited tactile or haptic feedback. This haptic feedback is limited to vibrations within user controllers. The issue with that is that vibrotactile feedback has a limited inability to convey forces effectively due to desensitization over time. It's good for conveying quick impacts or events, but doesn't do well with continuous forces, weights, and pressures, which are critical for us to understand when interacting with an environment. A good example is clicking a button or turning a knob. Without feedback on the resistance of the button or knob, it requires significant focus to ensure the action is done consistently and successfully when it's repeated. To provide one example of the huge impact that squeeze-based haptics could provide to the specific industry is related to the growing robotic surgery industry. Because the user or the surgeon doesn't receive feedback about the forces that they apply on the tissue via the tools in the virtual environment, it can be more difficult to develop an intuitive sense for precision tasks that require force and pressure information, such as suturing, which is shown on the right. Incorporating squeeze-based feedback can make these tasks more intuitive, increasing surgeon skill and reducing return to the operating room for patients. However, the market for haptic technology expands way beyond that, and it's been increasing since 2017. The number of users has jumped 10 times from 3.2 million users in 2017 to 33.2 million users in 2025, and is only continuing to grow. So given the growing industry and the importance of tactile immersion to the future of VR, we want to know, how can we advance tactile sensory immersion technology in virtual interactions? And I'll hand it to Ali to talk about existing solutions.
So let's look at the current state of the art. Haptic gloves. These devices are increasing in popularity, availability, and overall value. They offer whole hand feedback, however, are bulky and limit the user from interacting with physical objects in the real world. The Da Vinci 5 is a state-of-the-art for virtual interaction, haptics and robotic surgery specifically. They can provide force feedback to the surgeon at the console with high precision in toolhead position and received forces through proprioception. The device is extremely expensive, very specialized, and far more complex than other devices in virtual interaction. TASB is our closest inspiration. It's a research device out of the Mahi lab at Rice University. It is capable of squeezing the wrist as well as vibration circumferentially around the wrist. The device is supplementary and used to enhance the user experience. The device is heavily restricted in accessibility, and there were only a handful made for the Mahi lab. And as they've grown old, they have begun to fail, and with the lack of modularity and accessibility, they lack the ability to be repaired. This is where we come in. Our mission is to develop a haptic bracelet with squeeze and vibrotactile feedback to enhance human-computer interaction.
The solution that we came up with is the wrist. The wrist is a reliable and affordable wrist-worn device that provides both vibration and squeeze-based feedback for use in virtual reality and augmented reality. Here's a high-level overview of our different device components. All of our materials are either 3D printed or readily available from hardware stores. The typical face of a smartwatch is where we house our dual motors that actuate the squeeze. One concern we noted with the TASB and prior iterations of our device is that it was awkward to put on. To address this, our design features a 2-piece housing conjoined with a dovetail at the housing center for easy on and off of the device. We use a biocompatible TPU filament for our flex band. This flex band in the device as a whole accommodates wrist sizes from the 5th percentile of female wrists to the 95th percentile of male wrists. Vibrotractor modules are placed circumferentially around the band. We additionally have wiring for the control. Shown here is a high-level diagram of our anticipated system. An in-game event, whether it be pushing a button or drawing back a bow, will send a signal to both the VR headset and our control software. This software will then tell the central control located in the wrist device what action needs to be done, whether it be addressable vibration, squeeze, or both.
Now let's take a look at our current prototype's radial squeeze mechanism. Here we can see we have two DC motors mounted inside of our housing. On the DC motors are two spools rotating, which winds the cord around the spool to create either a squeezing or releasing effect.
From left to right, we have a schematic of our squeeze mechanism, a picture of our line routing, and a CAD of our inside view. Regarding the schematic, smooth pins line up circumferentially with attachment cases, which allows for a flexible cord to pass over. This cord enters the housing and is routed inside to spool into our two DC motors. Because the rollers are ideally spaced equidistant, when the motors apply tension to the cord via spooling, this translates the concentrated radial forces throughout the wrist. Having dual motors does add some complexity, so Didi will now talk about this.
For a radial squeeze mechanism in the prototype, we implemented a dual motor drive system using a dual H-bridge driver chip from Toshiba. This system communicates with our microcontroller via two PWM signals. To evaluate our performance, we designed a human wrist test model. This human wrist test model uses an outer layer of silicone to emulate human skin, a rigid inner shell to mimic human bone, and an embedded 6-axis force sensor to measure for squeeze forces and torques. This is what the test setup looks like with a device wrapped around the test rig. Our squeeze testing results met our target of 10 newtons of squeeze force. The testing was done using our prototype, so there are definite improvements we're planning to incorporate, mostly aimed at shortening that actuation time. The key change we plan to make is a motor improvement, opting for a higher performance motor that will deliver higher torque and speed metrics. Thus, we're now improving on the actuation speed with our current in-progress prototype.
Moving on to the addressable vibration system, we have 5 linear resonant actuators, or LRAs, uniformly distributed along the wrist device. LRAs are vibration motors that take in AC voltage to generate vibration along a single axis. A key aspect of our design is that we maximize modularity by having each LRA attaching to its own PCBs. So if one of them have a hardware failure or a connection issue, we can easily replace it without disassembling the wiring within the entire wristband.
Here we're driving an LRA with a haptic driver and a modular PCB. As we drive the LRA at different frequencies, all these different frequencies are reflected in changes of the surface of the water.
Here's the graphical design sketch of the vibration system. We found a specific haptic driver chip from Renesas DA7281 that can digitally drive the LRAs by utilizing I2C protocols. I2C communication protocol has data and clock lines that enable us to individually select and control the vibration pattern of each LRAs. The chip has 2 address pins that can give us a total of 4 unique I2C slave addresses. And to support a total of 5 to 6 LRAs, we decided to use 2 separate I2C bus lines from the microcontroller. The signal lines SCL SDA as well as VDD and ground will be daisy chained across the LRA modules, which are mounted on custom PCBs. So here is the design of our custom PCBs that integrate the haptic driver chip, and the dimension is 28 by 15 millimeters.
Is our block diagram for our central control system. As you see previously on our prototype right now, we don't have a centralized control system where we will aim to do that in the next stage of our prototyping. As you can see, we would like to integrate a game engine, which will trigger some event, both virtual feedback for the people, and also for the control software, which will send the commands to drive the I2C chip for the addressable vibration, and we'll also like drive the PWM using the motor to create the squeezing effect on the waistband.
This is a deconstructed version of our central control where the MSP430 drives our motor driver chip, which drives our motor. Then the chip also drives our LRA haptic driver chip, and it also communicates to our force sensor calibration unit.
All right, so to summarize our design, the wrist is a haptic bracelet that includes a modular design, a dual motor radial squeeze, and addressable vibration feedback. In the future, we want to fully integrate PCBs into the device so that all electronics are on board. We want to upgrade the motors for faster squeeze response time, and we want to integrate this device into a game engine. The wrist device is compact, affordable, multi-sensory, and has a centralized control system, as opposed to the existing haptic solutions we discussed earlier. And these improvements, we hope that the wrist will provide a cheap and accessible way to provide the squeeze and vibration tactile feedback for full immersion into VR environments. By doing this, we hope to push the widespread adaptation of this technology into VR environments, and this technology can also help accelerate haptics research and human-computer interaction by providing technology that's accurate, reliable, and cost-effective for experimental testing. We want to thank our mentors, Dr. Trevas, Dr. Woods, Dr. O'Malley, and Dr. Chase for their wisdom and guidance throughout these past few months, and then also Dr. Bowles for her presentation advice. We also want to thank Rice University and the Oshman Engineering Design Kitchen for providing us the resources to complete our project. Thank you.